Okay, welcome to day 2, part 2 on how cool water is, how the uniqueness and the coolness of water. So yesterday we talked about hydrogen bonding and the fact that water has in the molecule partial positive charges and partial negative charges. So the oxygen is partially negative, the hydrogen was partially positive. And then we also talked about the fact that those lone electron pairs on the oxygens, the ones that are not involved in bonding, create a situation where that slightly positive charge on the hydrogen of a neighboring molecule will actually adhere to and hook onto those lone electrons on that oxygen, creating what we call hydrogen bonds. So it's between the partially positive hydrogen and those lone pairs on that electron of the lone electron pairs on the oxygen. So those hydrogen bonds do a lot of really cool things and create a lot of really unique things when it comes to the water molecule itself. So first we'll talk about the states of water. Hydrogen bonding is responsible for that high boiling point of water. Water boils at 100 degrees Celsius. That's pretty high. Reason for that, it takes a lot of energy to break the hydrogen bonds to create the gas. Okay? To get it to go from a liquid state to a gaseous state, you have to break those hydrogen bonds. It takes a lot of energy to do that. So they have a very high boiling point. Most of water on Earth is liquid because the hydrogen bonds hold the molecules so tightly that they're not easily going to evaporate into a gas state. Obviously, yes, it can happen. I mean, we watch puddles evaporate after it rains, but our entire lakes don't evaporate. Okay, some water does. We watch the lake levels go down throughout the summer, but most of our water is able to stay liquid because you can't evaporate everything. There's not enough energy to do that. As water starts to cool, the molecules come closer together like any other molecule, and that density is going to decrease because as it comes closer and closer until it gets about 4 degrees. Water freezes at 0, okay? But at about 4, the molecules start to rearrange themselves, okay? So they start to organize, they form a very open arrangement due to the hydrogen bonding. So I kind of wanted to show this to you, okay? Imagine that in this beaker is ice. Okay, so my water molecules, they're all hooked together, okay? They're all hooked together. And you can see that there's air spaces in there, okay? That is what happens with real ice. You get air spaces. That's what makes the density less. That's what makes ice float. That's the reason it expands as it becomes a solid. Okay, so as they do this, they can form into this nice state. Now, interestingly enough, if I was to smush this and try to get it back to quote-unquote liquid, you'll notice my volume went down. So this would be more representative of the liquid state. Okay, so that just kind of gives you a little bit of an idea of that difference. And you'll notice in the liquid state, in this situation, there is not as much airspace. Okay, so it's less volume. So that's the main reason that those air spaces in there is the biggest reason why ice floats. Okay, why that density goes down, because you've increased the volume, the mass stays the same, but you increase the volume, so the density will actually decrease on ice. Surface tension. What is this? It is the force needed to overcome the interparticle attractions and break through the surface of a liquid. The interparticle attractions in the case of water is the hydrogen bonding. We said it's pretty strong. So the surface tension of water is very strong. That's the reason why they say if you were to, well, that's part of the reason why you would die if you jump off a bridge, okay? Because they say when you fall from those heights, when you hit the surface of the water, the surface tension, those forces that hold it all together are so strong, it's like hitting concrete. That's also why they say if you are choosing to go cliff jumping, There's a safe way to cliff jump and there is a very unsafe way to cliff jump. Okay, if you go cliff jumping, you should always come into the water feet first, into a pencil type dive, so that your feet break the surface tension of the water before your body enters into it. If you do it wrong, it's extremely painful because of that amount of force that's put on your body when you hit. Surface tension is very, very strong in water. The higher the surface tension of a liquid, the more resistant the liquid is to having its surface broken. Wax surfaces, you can see it beat up. So I do have a little demo I want to show you on surface tension. I'm going to use this little penny here. Okay, let me just double check and make sure that's in the screen. And I don't know if I did this lab with you guys before to demonstrate surface tension, but if I put drops on this penny of water, it will bubble up. Okay, you can actually hold quite a bit because of the strength of that surface tension, because all these water molecules are holding themselves together. See how many I can get on here. So this is surface tension. You can see there's a big bubble of water on the top of that penny, okay? Because all these water molecules are holding together. They don't want to break. Eventually it will. Oh boy. And then finally it broke. I put one too much. So you can see a little bit what I mean. They hold themselves together very, very, very tightly. Okay? Capillary action. Capillary action is, again, a result of interparticle attraction. So the water molecules are attracted to each other. They're going to move up from each other. They're going to literally create a line. Come on. With each other. Okay? So capillary action is this idea that this water molecule here adheres to this one, 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 and then finally you can see my water molecules, they start to move up. This is how plants are able to take water from the ground and put it all the way up in the leaves at the very top of a tree. This is how they're able to move the water against gravity. It's this idea of capillary action, this idea that the water molecules, again, because they're attracted to each other, they will be attracted to each other in the sides of the container, or in the case of plants, the xylem, and it will actually move its way all the way up, so you can see that. Okay. Meniscus. When we take our volumes in our graduated cylinders, I always tell you guys to look at that meniscus. Remember, you kind of get this little bubble that forms like this. Okay, and we're supposed to take our volume at the bottom of the meniscus. Here's my cylinder. Okay, this meniscus forms because the outer molecules are attracted to the container. Okay, and it starts to crawl up. So this is this idea here on the sides where those water molecules are trying to crawl kind of up the container because they're all kind of attracted to each other, and then also to the container. So that's why you get that kind of that bubble that forms, this meniscus that forms. Okay. So the movement is caused by water molecules being attracted to each other, cohesion. Okay. So they're attracted, they like each other, so they adhere to each other, cohesion. And to the glass molecules, which is adhesion, so it causes that upward movement. Okay, so they're attracted to each other and to the glass. And they can crawl up there, creating that meniscus, that bubble. Like I said, capillary action, this is super important. This is how plants can survive and move that water up their xylem to get it from the roots all the way to the leaves at the top. Specific heat. Specific heat measures the amount of heat, and when you're talking about energy, you're going to talk about it in joules. That is the unit for energy, so the unit here is joules. That is needed to raise the temperature of 1 gram of a substance by 1 degree. Okay. How much energy does it take to change 1 gram, 1 temperature? Okay, 1 gram of a substance up 1 degree. And this is Celsius. Every substance has its own specific heat, and water has a very high specific heat value. Again, because to get anything to change or move, you have to overcome these hydrogen bonds, these interparticle forces. So this means water must absorb or release more heat for its temperature to change by 1 degree. This is also part of the reason why water is a pretty good insulator. It's not going to change temperature very much. If you go to Duluth in the summertime and you go to the Miller Hill Mall at the top of the hill, it's warm, it can be super hot. You go down to Canal Park and it's like cool and it's comfortable and it's nice. Why? Because the water temperature on Lake Superior isn't going to change that much and helps cool off the general area. It's like a big air conditioner down right by Canal Park there. If you go by the ocean, if you live by the ocean, the temperature doesn't really fluctuate as much. The ocean helps regulate the temperature, keeping it pretty steady. Because to change the temperature of water, it has to absorb or release a lot of energy, a lot of heat to do that. The specific heat of water is actually equal to 4.18 joules per gram times whatever the temperature is. So that's pretty high. Okay, that's pretty high. The specific heat of water, like I said, allows water to serve as a heat reservoir that moderates the temperatures on Earth's surface. Without all of our oceans to help regulate our temperature on our planet, we would have very, very extreme temperature changes. So this, again, is super important for life to be here. And again, it's because of those hydrogen bonds and the idea that water doesn't want to give up and change very easily. It takes a lot of energy to do it. The heat of vaporization. Vaporization, what is that? That is the change in state of a liquid to a gas. To become vaporized is going from that liquid to the gas. How much energy does that take to make it happen? The heat of vaporization tells you that. Okay? It tells you the amount of heat required. During the vaporization of a liquid, interparticle forces must be overcome. So, therefore, vaporization of liquid is endothermic. It's heat absorbing. If this was my liquid water here, and I wanted to get it to go from a liquid to a gas, if I move my hands super duper fast, they will start to spread out. I'll use less because I have small hands. So you can see naturally sitting here by themselves, they're going to hook on to each other. That's those hydrogen bonds that naturally happen. But if I add energy to it, they will actually start to spread apart and away from each other. Okay? And that is what the heat of vaporization is. It's how much energy you have to put in. I had to put energy in to get these to come apart. They didn't do it naturally on their own. So it's endothermic. Energy needs to get put into the system to get that to happen. So it is endothermic, okay, heat absorbing. Condensation, I should have bolded that, sorry. Condensation is the formation of a liquid from a gas. Okay, we see condensation when you take a cold glass outside on a humid day in the summer. Your glass will sweat. We say sweat. That's actually condensation on the outside of the glass. It's the water vapor from the air that's condensing on that colder surface. So it's going to a liquid from a gas. That is exothermic. Okay, that's exothermic. For that to happen, energy has to be released into the system. Okay, you're going from a situation where you're moving really fast, those molecules are moving fast, and you're slowing them down. So that energy that gets released as you're going from fast to slow, it's called exothermic. Okay, energy is released. Last thing that's super cool about water. Water is the universal solvent. Okay. Most water on our planet is not pure. In the lab, we always use distilled water to make sure that anything else that's in there doesn't affect our results. But basically, every water you encounter, every drop of water you encounter on this planet is not going to be pure. Okay, if it's natural, unless it's gone through filtration systems. But just natural water is not going to be pure. It's going to have other stuff in it. It's difficult to keep pure because it's an excellent solvent. Okay, it can dissolve a lot of things. A lot of things dissolve in water. We know not everything will, but a lot of stuff will dissolve in water. Okay, all the acids, bases that we talked about, all dissolve in water, which is a good thing considering our body is mostly water and we need, like you guys learned, to regulate our blood pH and stuff like that, to digest our food. We need acids and bases in our body. It's a good thing they dissolve in water. Okay, that's a big part of why you need water in your body, is so chemical reactions can happen. It gives them that media for reactions to occur in. Its ability to act as a solvent is one of water's most important physical properties. That is why living things need water, because these chemical reactions that happen in our body all the time need the water, need that environment, need to be dissolved for it to occur. Okay. It is the attraction of water molecules for other molecules as well as for one another that accounts for those solvent properties. This idea of water being polar and having these slight charges is why every ionic compound will dissolve in there. Because you have those positive and those negative charges. Anytime you have slight charges, the ionic compounds are going to go, yay! There's slight charges here, slight charges there, and they just kind of freak out and they like go all over the place and they dissociate. Okay? They ionize, like we talked about in chapter 14. So that polarity of water, those slight positive and negative charges, are super important and why water serves as such an excellent solvent. And that is the end of section 13.1. You will be getting the guided reading tomorrow, and then I have another vocab thing you're going to be getting this week as well. And again, if you have any questions on anything, please let me know. See you guys.